The massive explosion is an idea that has laid out the framework for deciphering the universe, outlining the support of current cosmology. Additionally, Einstein's theory, known in cosmology course readings, states that the huge explosion occurred when the universe began its evolution, pointing to the origin of all matter, energy, and presence. This event occurred approximately 13.8 billion years ago and sparked the colossal universe we notice today, despite its lateness. Improvements in cosmology suggest that the colossal explosion was most likely not the absolute beginning. Rather, there could have been a stage prior to the enormous and comparable explosion, critical in shaping the universe. This pre-season is referred to as infinite expansion. Development is quite possibly one of the most interesting pieces of modern cosmology. It suggests that before the hot, dense time of the enormous blast, the universe experienced unimaginable, rapid, emotional growth. During this period, the universe was duplicating in size at an alarmingly rapid rate. To precisely show how absurd this expansion is, assuming the universe began smaller than an atom, it would have extended to become unfathomably larger than the entire universe we can see today, all within a minuscule fraction of a second. This extension takes a quadrillionth of a second. The stage lasted only a short time before assuming a crucial role in the formation of the universe. After the end of the inflationary phase, the motivation for this expansion was released into space, warming it up and making the particles of matter that make up everything we discover in the universe. In numerous ways, development is the precursor to what we call the immense blast. While the hypothesis of expansion is generally accepted in cosmology, it still has many unanswered questions. For instance, we don't yet comprehend the beginning of the expansion, what brought it to an end, and how long it lasted. These unanswered questions are crucial for a better understanding of the starting point of the universe. Prior to evolution, the universe was in a stupendous state, a dense, small area of matter frequently referred to as a singularity. From this singularity, development began and ultimately resulted in the arrangement of atoms, stars, and galaxies. The possibility of the colossal blast as the start of everything is engaging, but present-day cosmology proposes a more complex picture. Some hypotheses suggest that the universe went through a phase before the gigantic blast. During this stage, expansion made the universe grow at an incredible rate, its size increasing by a factor of 1 trillion in a fraction of a second. This quick expansion was fueled by a bizarre energy structure that filled the void of space. Once the energy was depleted, the expansion ended. This process converted that energy into particles, warming the universe and prompting the hot, dense state we call the gigantic blast. This inflationary stage was cold and empty, but it set the stage for material production and the universe we see today. One of the more current theoretical considerations in cosmology is the idea of timeless expansion. This hypothesis proposes that expansion did not end simultaneously everywhere. Rather, it stopped intermittently, creating a wide range of pockets, each of which could be a universe in its own right. Our universe could be only one of these pockets. According to eternal expansion, there could be a limitless number of such universes, each with its own configuration of physical laws and constants. This is where the possibility of the multiverse becomes an integral factor. The idea that our universe might be one of numerous, or even an endless number of universes. If this theory proves correct, it could explain why our universe is so finely tuned for life. In this multiverse scenario, every possible combination of physical laws could exist in various universes. We just happen to live in one where the conditions are perfect for stars to form, and for elements like carbon and oxygen, fundamental to life, to exist. While hypotheses like eternal expansion and the multiverse keep an open mind, the possibility of expansion itself is grounded in solid observational evidence. The strongest support for expansion lies in the cosmic microwave background radiation, CMB, the oldest light in the universe. The CMB was emitted approximately 380,000 years after the colossal blast, when the universe had cooled enough for atoms to form. At that point, the universe became transparent, and this light has been traveling through space ever since. By concentrating on the CMB, cosmologists can essentially take a baby picture of the universe. This light provides crucial information about the universe's beginnings and helps researchers understand what took place following the enormous explosion. It also offers strong support for the inflationary model. One of the most significant discoveries came from the European Space Agency's Planck satellite, which captured detailed images of the CMB. These pictures show subtle variations in the temperature of the early universe, variations that align with the predictions of inflationary theory. This evidence supports the idea that expansion is not merely speculative but a significant piece of how we understand the universe's origins. Comprehending the enormous explosion and what came before it requires unifying two of the most important theories in modern physics: Einstein's theory of general relativity and quantum theory. General relativity describes the structure of the universe at a cosmic scale, including the behavior of galaxies, stars, and planets. Quantum theory, on the other hand, describes the behavior of atoms and molecules at the smallest scales. To answer key cosmological questions, such as what the universe is made of and where it came from, researchers must develop a theory that unites these two frameworks. This unified theory could allow us to understand not only the colossal blast but also all the conditions that caused it. One of the most astonishing aspects of the universe is its size. The majority of distant objects we can see are approximately 47 billion light-years away, indicating that the visible universe is around 94 billion light-years across. This might appear to be abnormal, given that the universe is just 13.8 billion years old. How could the observable universe be bigger than the time it would necessitate for light to navigate it? The answer lies in the universe's age and how it has grown over time. As the universe expands, the increasing distance between objects creates regions that are farther away than the time it would take for light to reach us. Most researchers accept that the universe spans a great distance. The discernible universe is, in truth, just the part we can see, constrained by the amount of light and the time required for it to travel since the Big Bang. There might be huge areas of the universe that we will never be able to see at all. While it's conceivable the universe is endless, the inquiry remains: is it truly infinite? Anything beyond the scope of the visible universe remains uncertain. If there is no end to the universe, it would simply carry on indefinitely. No matter whether the universe is finite or infinite, it might not make sense to talk about anything beyond it. Beyond would imply something outside space, which may not have any physical meaning. Similarly, the beginning of the universe is a topic that demands deep attention. So too is its inevitable end. The best current estimate is that the universe will keep expanding perpetually. This is attributed to a bizarre phenomenon: dark energy, which causes the universe's expansion to rapidly accelerate. Prior to the emergence of dark energy as a key concept, scientists believed that the universe's expansion would eventually slow due to the gravitational pull of matter. There was even the possibility that the universe could stop expanding and begin contracting, resulting in a big crunch. But dark energy now appears to be tearing the universe apart more and more quickly. If this acceleration continues, the universe will continue to grow endlessly, ultimately reaching a state where galaxies drift so far apart that they effectively isolate themselves. In this scenario, the universe would become cold, dark, and exhausted. Stars would burn out, matter would decay, and galaxies would drift apart, eventually falling into ruin. This is referred to as the Big Freeze or heat death of the universe. The narrative of the universe, from the enormous blast to its possible end, is one of the most improbable, yet critical and complex stories in science. Despite the fact that we've gained an extraordinary amount of knowledge about the origins of the universe through the theory of expansion and the study of the cosmic microwave background, many questions remain. For example, what caused expansion to begin in the first place? Is there space beyond the visible universe? Could a multiverse exist? And how many additional universes might there be? As researchers continue to explore the cosmos using new ideas and advanced hypotheses, they attempt to connect quantum mechanics with general relativity. The journey to comprehend the universe's mysteries continues. Every new discovery brings us closer to answering profound questions about our existence. The investigation into the structure and origins of the universe is more than just a scientific endeavor. It also raises philosophical inquiries about existence, reality, and our place in the cosmos. One significant area of interest in cosmology is the role of dark matter, which is believed to make up approximately 27% of the universe's mass energy content. Unlike normal matter, Dark matter does not absorb or reflect light, making it invisible, detectable only through its gravitational effects on visible matter. Understanding dark matter is crucial to explaining the development and behavior of galaxies. Ongoing studies and observations have provided insights into dark matter's properties, but its exact nature remains elusive. Several candidates have been proposed, including weakly interacting massive particles, WIMPs, axions, and other exotic particles. Yet, so far, no direct evidence of dark matter particles has been found, and the search continues. This pursuit combines terrestrial experiments, astrophysical observations, and simulations that model how dark matter influences the large-scale structure of the universe. Another major area of exploration is dark energy, the force driving the universe's accelerated expansion. Dark energy accounts for about 68% of the universe's total mass energy. Its discovery was unexpected and has sparked numerous hypotheses, including the cosmological constant and dynamic fields like quintessence. Understanding dark energy is essential, as it will determine the ultimate fate of the universe. Researchers are studying its effects on cosmic structures and trying to determine whether it remains constant over time or evolves. In addition to dark matter and dark energy, the study of large-scale structure formation provides valuable insights into the history of the universe. Observations of immense clusters and filaments of galaxies, influenced by gravity, help explain how the universe's intricate structures formed over billions of years. Supercomputers are used to simulate these processes, aiding researchers in their understanding. Astrobiology also intersects with cosmology, as scientists investigate the conditions necessary for life beyond Earth. The search for exoplanets, planets orbiting stars outside our solar system, has intensified, with thousands discovered in recent years. Some of these exoplanets exist within their stars' habitable zones, where conditions may be right for liquid water to exist. By studying these distant worlds, researchers hope to learn more about the potential for life elsewhere in the universe and the factors that make a planet habitable. Finally, the role of fundamental physics in cosmology cannot be overstated. The quest for a unified theory that connects general relativity and quantum mechanics continues. Theories such as string theory and loop quantum gravity aim to bridge this gap, offering explanations for phenomena like black holes in the early universe. As technology advances, so does our ability to observe and interpret cosmic phenomena. Space telescopes like the James Webb Space Telescope are transforming our understanding of the universe by providing unprecedented detail of distant galaxies and cosmic events. With each groundbreaking observation, we move closer to unraveling the mysteries of the universe's formation, evolution, and ultimate destiny. The study of the cosmos is a complex web of scientific inquiry and philosophical reflection. From the fundamental forces that shape large-scale structures to the search for extraterrestrial life, our exploration reflects the enduring human spirit and curiosity about the universe. As we strive to answer these significant questions, we gain a deeper appreciation for the vastness and intricacy of the cosmos.